presenter is Çağdaş from Katip Celebi University.
Thank you very much for the introduction. Welcome everyone. Today my colleagues and I are excited to share our research, SmarCyPad, a smart seat pad for cycling fitness tracking, leveraging low-cost conductive fabric sensors. It's a collaborated work between the University of Tennessee, Knoxville, and myself. I am a former Microsoft employee and currently assistant professor at İzmir Katip Çelebi University, Turkey. Indoor cycling, virtual cycling has been increasing its popularity in recent years as it brings convenience, fun, and competitiveness. Especially during the pandemic, virtual exercise has gained considerable attention. Zwift, the most popular immersive indoor cycling app, has more than 4 million users currently. The immersive experience of virtual cycling is often hampered by the limited feedback on users' posture and measurements. For instance, the movement of the avatar's body in the virtual scene is not synced with the cyclist's pedaling and does not reflect their actual riding postures. Accurate riding posture reduces the effect of the aerodynamic drag. Additionally, many virtually cycling apps only provide basic training insights such as speed. Hence, cycling fitness tracking is essential to track cyclists. Commercial on-bike sensors for cycling fitness tracking are attached to the bike's wheel hub or crank arm and only monitor the cycling cadence and speed. Computer vision-based approaches utilize a camera placed at the side of the cyclist and are prone to errors due to the light conditions, occlusions, and raise privacy concerns. On-body sensor approaches can track riding position or joint angles. However, they would require inconvenient setups and affect cycles' mobility and comfort. To address these limitations, we propose SmarCyPad, a smart cycling fitness tracking system in the form of a seat pad that can be easily deployed on any bike saddle. It can continuously and unobtrusively track 5 metrics: cadence, per leg stability, leg strength balance, riding position, and knee joint angle by utilizing its fabric-based pressure sensors. We use pressure fabric, Velostat, a material that its resistance drops when the external pressure is applied. We observed that more layers can endure a higher level of pressure and place 3 layers of Velostat between 2 layers of Faraday fabric to create the sensor. We utilize 2 channels with 1 channel per leg. Each channel is composed of the voltage divider stage and the analog reading layer, utilizing resistivity of conductive threads to capture the pressure distribution of the saddle. We utilize 3 fabric sensors connected to a voltage divider circuit crafted using zigzag-shaped conductive threads to capture pressure distribution on the saddle by altering the voltage readings, Vout, as the pressure is applied to the different resistors, RL1, RL2, RL3, moving the Vout closer to respective voltage readings, VA, VB, and VC values. Manufacturing process is displayed in this figure. We use suede as the material for the seat pad. The conductive threads are stitched on the suede as following the circuit diagram. Insulating tape is used to prevent short circuits, and Velostat pieces are connected utilizing non-conductive threads to the voltage divider layer. We then stack 2 layers together and connect to VCC. As common bike saddles share similar sizes, we standardize the sensors placement for all saddles. Our system can be divided into 3 parts: cadence, stability, and balance estimation, riding position classification, and knee joint angle regression. We first get to the cadence, stability, and balance by leveraging signal processing algorithms. We perform low-pass filtering on the raw sensor data and remove high-frequency components. As cycling activities show a periodic pattern, we apply a peak detection algorithm to detect each cycle period. For the left channel, an ascending part in a single pedaling period indicates the left leg pedaling, and the descending part indicates the right leg pedaling. The pedaling time further can be determined, cadence, per leg stability, and leg strength balance. Now, let's discuss the riding position classification. The filtered sensor data is segmented into 1-second frames that serve as the input of the CNN-based classifier. The network contains a 1D CNN-based feature extractor and a fully connected layer of position classifier. We add convolution block attention module, CBAM, after each convolutional layer, refining the future representations. As the sensor readings for each person have unique pattern, we fine-tune the pre-trained classifier via unsupervised supervised domain adaptation to make it learn more domain-independent feature representations. Finally, we add additional domain discriminator with fully connected layers after the feature extractor, which aims to distinguish whether the sensor data is from the source domain or the target domain. Knee joint angle regression contains two sub-blocks: generic regressor training, in which we recruit a single cyclist to train a generic regressor, and testing phase, in which any cyclist can directly use the generic regressor without training required. We then derive the cyclist knee joint angles using open pose, a CV-based approach. The sensor signals and the measured joint angle for each cycle are mapped via linear regression. In the testing phase, the cyclist must first perform one-time knee flexion extension angle measurement to get their unique knee flexion and extension angles. The filter sensor signal passed the same pre-processing procedures in the training phase, and the normalized signal is fed into the generic regressor to get the normalized knee joint angle. We recruited 15 cyclists to evaluate the performance of SmarCyPad on 3 bike saddles with different shapes and sizes. Each cyclist is asked to cycle for 15 minutes with 5 different riding positions. All cyclists achieved comparable low errors for cadence estimation. The average mean absolute error for all cyclists is only 1.13, and the RE is 1.70%. Additionally, we observed that SmarCyPad can accurately detect cycling imbalance. Our measured RMS SSD achieves high consistency with the cyclist difficulty ratings. Specifically, all participants feel it is relatively easy to maintain the speed at 10 mph, and the corresponding RMSSD is also low. However, all cyclists give 15 mph a hard rating over 4, and the RMSSD also increases accordingly. For riding position classification, if the training and testing data come from the same cyclist, the average accuracy is 96%. If no labeled data or 1 minute's labeled data is available during the training, we observe that without domain adaptation, the average accuracy is close to 50%. However, the average accuracy largely increases to 77% with unsupervised domain adaptation and 93% with only 1 minute labeled data. We use one participant data to train the generic knee joint angle regressor. We achieve an average MAE of 9.5 degrees and average PCC of 87%. We observe that the reconstructed knee joint angles are highly correlated and strictly synchronized with the ground truth. In conclusion, in this project, we propose SmarCyPad, the first smart seat pad for cycling fitness tracking. We manufactured the sensors and the prototypes from scratch, and implemented sensing prototype can be generalized on any saddle with a low-cost budget. We introduced a novel approach to improve the cyclist's immersive experience and cycling performance. And we have conducted the experiments with 15 cyclists, different positions. Thanks for listening.
Thanks. Çağdaş from Colombia, thank you so much for your great talk. So, can you please share more insights on the rationale behind deriving the knee joint angle from the saddle pressure? Because intuitively, I feel like this pressure is very sensitive to the sitting position, or even for the same people for the same person, when you are cycling, you are changing position oftentimes, right? So, is there any insights on the rationale? And
so that's why they had to be fine-tuned based on the rider's riding skills. We have to provide some more information about it. Yes, I agree. Everyone's knee angles change, and the measurements also on the SmartPad changes as well. But that needs to be fine-tuned, and it can actually measure the distribution of the pressure, basically. So that's the insight.
thank you.
That's okay.
I was fascinated that you could determine the knee angle from the seat pressure, but are any of you authors cyclists?
They became one.
Okay, because a vast majority of the time, you're out of the seat, particularly if you're indoor cycling. You do a lot of it. So why didn't you, instrument the compression shorts to do the same thing?
Yeah, because the thing is, they require extra, equipment. We try to avoid.
Sure, that's fine.
Yeah.
It's a challenge, I get it.
It's a good idea. I frankly agree.
Well, but it's important because the majority of your time, you're out of the saddle.
Well, I'm not a rider per
Okay,
se,
yeah.
so I don't know much about it. Thank you very much.
All right, let's thank the speaker again.